Introduce permutations today. We're also going to introduce something called the fundamental counting principle, define what a permutation is, introduce factorial notation, and problem solvings involving permutations. We're going to break this up into 2 days, so we'll probably just get through about half of what we're going to in this entire section today. So as an investigation, permutations are like about trying to figure out how many possibilities can occur with a certain set of outcomes. So if you're deciding for school tomorrow, which we all often do, we go to our closet and try to figure out what if we considered there were 3 t-shirt options. We could wear a red t-shirt, a black, or navy. The pant options, we could either wear jeans or khakis, or the shoe options would be our blue loafers. So looking at the tree diagram shows all the possible different outfits that are possible. Shirt with jeans with my yellow shoes. Or I could wear my red shirt with jeans with my blue shoes. Could wear my red shirt with khakis with yellow shoes, red, khaki, blue, black, jeans, yellow, and so you kind of get the idea here, right? So all the possible combinations, or not combinations, but possible outfits would be 12 if I counted these up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So what the fundamental counting principles allows us to do, because we don't want to create this tree diagram for every single possibility, is we can simply take the number of shirt options we have, which is 3, and then multiply it by the number of pant options we have, which is 2, and then multiply it by the number of shoe options we have, which is also 2. So 3 times 2 times 2 equates to 12. So this would be a quicker way in order to determine the number of outfits that are possible. Okay, so as a definition, the fundamental counting principle, if one task can be performed in A ways, so that would be our, and a second task can be performed in B ways, which would be our pants, then the 2 tasks performed together would be A times B. And then if there's 3 tasks, then you'd multiply it by C ways and D ways and so on. Okay. So as an example, it says the best burger joint in town has a build your own burger option on. The chart below highlights the options for building your burger. So here are the options for a bun: white, whole wheat, or gluten-free. Patties, you could get a single, double, triple, or a veggie patty. And cheese, you could get no cheese, cheddar, Swiss, Havarti, or mozzarella. Okay, and we're only going to choose one of these options for each one. It gets into a whole other scenario if we're starting to pick 2 out of them. How many can possibly be made if you choose one option from each category? So very simply, there's 3 possibilities for my times 4 different possible patties times 5 different possible cheese options. So this would be a total of 60 different burgers can be made. Okay, and then as we start to get more comfortable, we start to get into like restrictions. So if, let's say, I can only eat gluten-free, how many burgers can be made if the bun is gluten-free? So from the bun option, I only have one option. So this would now be a 1 different options for my patties times 5 different options for my cheese. So if you had to choose a gluten-free, there's only 20 possible burgers that can be made. Okay. So this is the definition of a permutation. A permutation is an ordered arrangement or sequence of all or part of a set. It's important to remember that the order of the arrangement matters. So when we're talking, the order in which we put things matters. Okay. So the next thing we're going to introduce is something called factorial notation. So for any positive integer, the product of all the positive integers up to and including n are the following. So for example, factorial notation is like an exclamation mark in English. It's called a factorial notation in math. So if we took some number, the factorial notation of that number, this means is we're going to take that number times 1 less than that number times 2 less than that number, times 3 less, and so on until we eventually get down to a value of 1. Okay, so for example, if I took 4 factorial means I'm going to take 4 times 3 times 2 times 1, and I'm always going to stop there. So if at 1 I'm going to stop. So 10 factorial, 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So over time, we don't want to type all of this into our calculator. We're actually going to, there's a factorial sign that we would want to use. All right, so example 2, it says, how many permutations are there of the letters in the word Kelowna? So what this means is that these are like Scrabble tiles, and I want to figure out how many different ways I can arrange these letters if I have to use all of them once. So I can't double them out. I'm using that K. Once I have the E, I have to use the E. So I'm using all of these letters once. I don't have to create a word from the letters. I just have to figure out how many arrangements are possible. So if we were talking about, we have all these letters like in a bag, and then I pull out my first letter. So how many possible letters could go into this first position for my arrangement? Well, there's 7 to choose from, so I have 7 possibilities for that first. Well, I've used one of those letters up. Let's say I pull the N, or the N, and the N is now here. I'm going to go back to the bag. How many possible tiles are left in the bag? There's only 6 left in the bag. Times, and we're doing a 7-letter arrangement, so 1, 2, 3, 4, 5, 6, 7. I go back to the bag. There's only going to be 5. Now there's only going to be 4. Now 3. Now 2. And then finally there'll just be 1 tile left in the bag. So if I multiply this, all these values up on my calculator, I get 5,040 arrangements or permutations. So arrangements and permutations are kind of like the same thing. Okay. Or a quicker way to do this on your calculator is simply type in 7 factorial. So on your calculator, what you want to do is you want to type in the number 7. You go over to this PRB location, and here is your factorial symbol, so number 4. So I put factorial, I hit enter, my answer is 5,040. All right, so these first few examples are fairly straightforward. Moving on. Example 3, it says determine the number of distinguishable 4-letter arrangements that can be formed from the word English. Okay? If A, letters can be repeated. So what I'm creating here is I'm creating a 4-letter. Again, I'm throwing all of these letters, Scrabble letters, into a bag, and I'm pulling one out each time. But every time I pull one out, I get to put it back in the bag and pull again, because we can repeat letters. So here, how many letters are possible for my, well, there's going to be 7. Times, I'm putting that letter back. How many possibilities for the second pull? Would be 7. And then the third pull, 10 times 7. So technically, if we can repeat letters for a 4-letter arrangement using the letters of English, 7 to the power of 4, or 2,401 arrangements. So recognize mutations. We will always assume repetition is not allowed and unless it says otherwise. No, you have to use, once you've used up a letter or a task, that task is done. So now question B, it says no letters can be repeated and there are no further restrictions. So again, I'm creating this 4-letter arrangement. There are 7 letters in the bag. I'm going to pull up my first letter. So how many letters are there in the bag to pull from? There would be 7. Times, I'm not allowed to repeat letters. There would be 6 left to pull from, times 5 left, times 4. And because we're only making a 4-letter arrangement, we're going to stop at that point. So 7 times 6 times 5 times 4 is going to equate to 840 arrangements. All right, so now we're going to start looking at some restrictions. It says the first must be an E. Okay, so we have to pull the E. So we're not taking a chance at pulling the E. This first letter has to be an E. So we're specifically making this an E, taking that out of the equation basically. There's only one E to choose from, so this would be 1 times, and then how many letters would be left in the bag? Well, the E's already gone. There's going to be 6 letters left, and then I'm going to pull the next letter and then the next letter. So this is going to equate to 120. Okay. The arrangement must contain a G. Okay, so take note of these. So this arrangement has to have an E, but the E has to be the first letter. Here it just says must contain a G. So the G could end up in any one of these locations. So I'm still going to draw out my 4 locations, right? So let's assume G is potentially in the first position. Well, I would get the same answer as if it. So there's 120 ways for G to end up as the first location. But what if the G was in the second location? Well, this would be different. So now the G is here. There's only one D to choose from. Now there would be 6 possibilities here times 5 times 4, which is again 120. So technically, how many positions could the G occur in? Would be 4 different positions. I want to take 120 because that would be one of those positions, and then times it by 4 positions. So my answer would be 480. Last one, the first and last letter must be vowels. All right, well, what are our vowels in the word? E and the I. So one possibility is the first letter could be an E, which is one possibility, and the which is 1. So I've used up 2 of my letters. That would only leave me with 5 letters remaining. So this would be 5 possibilities that could go here times, which would be 20. But then we have to consider, well, technically, does the E have to go first and the I go last? No, these could be swapped. The second possibility would be this, where the I could go here and the E could go here, and then this would again be 5 times 4. So 20 ways for this to occur, 20 ways for this to occur. If I add the 2 together, there's 40 possible ways the first and last letter will be vowels. All right, example number 4. It says car number plates in an African country consists of a letter other than I or O. So it consists of one letter other than I or O, so we can't include I or O, followed by 3 digits, the first of which cannot be 0, followed by any 2 letters not repeated. How many different car number plates can be produced? All right, so what are we talking about here? So we have a car plate. So the first position, so that's our first position, is followed by 3 digits, 1, 2, 3, and then after that it's followed by 2 letters. So we're filling in a 6 position license plate. So it says the position has to be a letter, but it can't be I or O. So this is our restriction, can't be I or O. Well, there's 26 letters in the alphabet. We can't have an I or O here, so that would leave 24 possibilities that would go here. Times 3 digits are going to be any digit, but the first cannot be a 0. So this cannot be 0. So that would leave 1 through 9. So there's 9 possibilities for that. It doesn't say anywhere that the digits can't be repeated. So now this next position could be anything from 1 to 9, but it could also be 0. So that would be 10 possibilities times 10 again, because we're allowed to repeat digits. It doesn't say anywhere that we can't. And then by any 2 letters which are not repeated. So I don't think these restrictions has anything to do with the front letter. Just these 2 letters can't be repeated. and I can include. So there's 26 possibilities that would go here, but I can't use that letter. That would only leave me with 25 possibilities left. So when I multiply this all out, I get a value of 14,040,000 number plates. Okay. All right, example 5. It says consider a 6-digit numeral. So a number. Note that 022713 isn't necessarily a 6-digit number. It's actually a 5-digit number, because when 0 is in the front, it actually doesn't take place of a place value. So this would be a 5-digit number. So I want a 6-digit number. So what does it tell me? It tells me that the first number cannot be a 0. So that's my restriction here. All right, so I'm going to draw out my 6-digit number. We already know the first number cannot be 0, otherwise it won't be a 6-digit number. And then it says how many odd-digit numerals have no repeating digits. So I can't repeat any digits. It has to be an odd-digit numeral. So what makes a number odd? Is the last place value of the number. For an odd number to be odd, this last place would have to be odd. So the possibilities that could go here would be a 1, a 5, a 7, or a 9. So what you want to do is you always want to start with your restrictions first and then fill in everything after. So I'm going to start at the end here and say, well, this last digit has to be either a 1, a 3, a 5, a 7, or a 9. That's 5 possibilities that could go in that position. So now I'm going to come back to the front. I've used one of these up. I don't know which one. Let's say the 9. So that leaves only 4 odd numbers and technically 4 even numbers, right? Because there's a total of 10 digits. I can't use 0 here, and I've used one of the numbers up here. So that would leave me with 8 to start my number. Times this second position, I've used 2 numbers up already, and there's 10 digits. I can now include 0 here. So 10 minus 2, this would also be an 8, because now I can put a 0 here. And then I can't repeat digits, so there'd be 7 left over, times 6, times 5, times 5. All that up, we get 67,200 numerals. So that's how many numbers can be created that are 6 digits where it would be an odd number. All right, how many even 6-digit numerals have no repeating digits? So this one is a little bit tricky, because what we have to consider, because there's a conflict between this last spot and this spot, because technically this could be a 0, a 2, a 4, a 6, or an 8. Right? Because it's an even digit number. So for something to be even, this position has to be an even number. Either a 0, a 2, a 4, a 6, or an 8. So we have to consider, well, this and this conflict each other a little bit. So what we have to consider is 2 different possibilities. Because what happened if this number was actually the 0? Well, that would be one possibility. Let's assume 0. We're putting 0 in this position. So we're going to ignore all these. And well, we've used 0 up. We know this can't be 0, but we've already used it here. So technically there's 9 possibilities for this position. And then times 8, times 7. So this would all work out to 15,120 ways. But then we consider, well, what happens if this is not a 0? It's the 2, the 4, the 6, or the 8. Well, that would mean there's 4 possibilities here. This also cannot be a 0, so this is only going to be 8 possibilities, right? Just a number up here. I can't use 0 here. There's 10 digits to work from, so that would be 8. So this is why you have to do two different scenarios, because this first term, first place, is going to depend on what's happening over here. Okay, so we have to consider, well, what if it's 0? If it's 0, then this would be 9. What happens if it's not 0? Then this first place would be an 8. And then we've used up 2 digits, right? One of these and just another out of a total of 10. So there's going to be 8 digits left. Times 6 times 5 times 4. So this value would be 53,760. And then I'd want to add these totals together to give me a total of 68,880 numerals. Okay? All right, let's move on to one more example and then we'll stop there for. So the number of permutations n of different objects taken r at a time can be written as the following formula. So this is our formula for permutations, where we permutation r. We're working with n number of objects, and we're taking r number of objects from that. And as a formula, this could be written as n factorial over n minus r factorial. So, for example, if we were asked to solve for n, if n permutation equals 3 equals, this is a typo, this should say 56. What we wanted this formula in order to solve for n. So if I were to substitute this information into my formula, I would get divided by n minus 3 factorial. And that is going to equate to 56. So what I want to do here is I want to be able to solve for n. So we got to go back and think of what an n factorial means. It means that we are starting with the number n, whatever it is. We're going to multiply it by the previous number to that, which would be n minus 1. Multiply it by to the previous number of that, which is n minus 2, n minus 3, and technically I'm going to continue this all the way down to a 3 times 2 times 1. What does this represent? Well, instead of starting at n, starting at an n minus 3, but the concept is still the